Hello and welcome. My name is Danny Quinn, and if afterwards you want to chat to me, my Twitter handle is Danny C. Quinn. What I'm going to be talking about is language in maths. I love maths. I love teaching maths. I've been teaching it for 10 years. I've been a head of department in 2 different schools. And one of the things that I have found has made the biggest difference to helping children to unlock maths and to make the classroom more rigorous and children more successful has been counterintuitively a focus on language. You may know this quote from Wittgenstein, "The limits of my language mean the limits of my world." Without wanting to go deeply into what he meant, I have messed it up a little bit to suggest that I think the same is actually true for maths, that the limits of the language that we give the children are the limits of the world that they can actually think in mathematically. What I want to look at is how do we give that language to the children, and it goes far beyond simple strategies around vocabulary or talking to your partner, and how do we actually break that down. A book that I really love, and all of his work I really find amazing, is by Paul Doyle, is I can't say it very well, Get Better Faster. What he really focuses on is how do you actually do things to get high expectations and rigor in your classroom. We know that high expectations and rigor come from having those beliefs, believing all the children can do it, but that comes from the culture. But where does that come from? That comes from the repeated norms, what you do every day, what the children expect each other and you to do every day. And where that comes from, what I want to focus on with you, is the strategies and techniques. So what is focused on in Bambrick's and Toya's work, and what I want to focus on today, is in order to get the big picture thing that we want, which is a great culture and great beliefs around what the children can achieve and what they believe in themselves, is we have to begin with the small work of the right strategies, the right techniques that we can actually implement to make that happen. So just to put this in context with some other things that you might have read and hopefully, like me, really enjoyed, is, for example, in Ed Southall's book, which I really recommend, he talks a lot about why the maths is true. So, for example, you're showing something to the children or to adult friends, and they want to know, well, why is it true? And also you don't want to just teach instrumentally or formulaically. This fits in the spectrum of that, where you're not just looking at the why, but how to get the children to comprehend and to be able to articulate the why, which will be the focus. You may also have enjoyed Craig Barton's second book, Reflect, Expect, Check, Explain. What I'm going to focus on is what are the techniques that actually get a good explanation from the children. So not just you tell them what to say, they say it back. What are the broad techniques across the spectrum that are all small little actions that add up, that get the kids to be able to have strong expectations and to be able to articulate them really well, and to articulate when they're surprised and so on. So there are 3 things we're going to look at for improving language use in maths. One is a really big picture idea that was the most transformative for us in my last department, which is moving from the specific to the general. That means rather than looking at an example with children and talking about that example, talking about the general ideas of that example. I'm going to break that down with lots of examples in a minute. Some specific techniques for refining your instruction, and then a smaller thing at the end for my own reflections and experiences on how you can implement this for yourself or with your team. So let's look at moving from the specific to the general. I would say, and this image is just to remind me to say this is very much an investment. Doing this is something that you may get some quick wins or see some quick improvements if you start doing this to your pupils, but it's not going to be that like you change one thing and then the children have changed. What you're trying to do with this is really change the norms and their expectations of what, and your norms and expectations of what you expect to hear and what they expect to say to you, what they expect you will accept from them. You know, obviously you're not going to reject things they say, but what they know the new standard is in your classroom. So the things I'm showing you here aren't something for this first bit, are something that is a goal to work towards, and I'm going to hopefully successfully show you some techniques to break down moving towards that goal. But I would say this is an investment that reaps huge rewards and is completely transformative in both what the children say and the confidence with which they say it and how that affects their reasoning, but it is a long-term investment. So I say that just so you can have that in mind, thinking what time frame you're trying to work towards to be successful at this. So the first step of moving from the specific to the general is, when you're talking about an example with the students, focus on the strategy for that example, not the steps. So let's say you have this question here, calculate the area of this triangle. Setting aside that obviously there are 2 ways you could do it, so you could find the perpendicular height coming from 10. Setting that aside, here's the specific. This would be a typical thing you might either hear a child say or the teacher say. I'll let you read it. You feel like, oh, I've been really rigorous, I remember the units. This would be a more generalized explanation. This is an example of what I mean about the time investment. So to draw attention to the specifics is that for the first bit of the reaction that either the child is giving or the explanation that this teacher is giving, it doesn't focus on the specific numbers involved. And that's a really good trick to help you think, am I talking about the strategy or the steps? Is thinking, if I'm talking a lot about the numbers specific to this question, I'm probably being too specific to this example and not generalizing enough. So first thing is being clear, what am I finding? The area of a triangle. And therefore, obviously this assumes you've already talked before about why this is a formula for area, assuming that that work's already been done and the children have that sense of understanding, that conceptual understanding that is established. What formula do I actually need? Therefore, I need width and I need perpendicular height. And as clarified, I need two lengths that are perpendicular. That's the critical thing. Another thing that's been clarified is that they span the whole shape. This width is the full width. This height is the full height. Clear use of technical vocabulary. So obviously, in a desire to be sort of folksy and accessible to children, might say, oh, we'll whack them in there, we'll pop them in there. And maybe if you've gotten to the point that the kids are really great with their algebra, you can say that playfully. But I'd say until the children are really secure, you actually do want to always use consistently the same technical vocabulary, because I don't know, it almost sounds naughty, like whacking and popping, like it could kind of almost mean anything. So until it's very clear to everyone what's going on, I would always stick with the unambiguous and quite short technical vocabulary, because then the children know what to expect, and you can also check that they are very clear when you ask for them to explain back what's going on at that stage, the calculation. It's simplified, and then even at the end is clear, why have I picked the squared units? Because I'm measuring area, that's two-dimensional, so on. So just a lot more things that now transfer to more questions. So looking at some examples of the difference between steps and strategy is generally steps tend to be descriptive. So it's almost like a David Attenborough narrator over the example saying, and now we're timesing by 4, and now we're having it, and now we're adding them up. So it's a lot of narrative and description, where strategy is more about why you're doing different things. This is what I'm using, and it's general, this is why I'm using it. Generally, if you're being too specific, if you're being specific and focused on steps, there'll be a lot of mentioning of the specific values in the question. If it's more strategic explanation, we focus on general names for the values, the width and the perpendicular height, for example. A difference, and this is where this time investment comes in, is, are you focused on quickly getting to the answer, we're done, or are you focused on how did I know to do that? An important thing that I think is a really big difference in terms of the building towards the pupils' ultimately sense of independence and ownership and their own sense of autonomy is, do the children know it's correct because the teacher said so, or do they know it's correct because it's the result of a chain of reasoning that they also believe in that chain of reasoning and articulate it for themselves and feel convinced about it? And the most important thing for us thinking about, if you're thinking about particularly the children perhaps struggling with AO2 or AO3 problems at GCSE, is when you show examples that are focused on the steps and the specific, it tends to only transfer to identical problems, the exact same shape, in the exact same orientation, when just the numbers changed around, versus strategy explanations will transfer more to a broad class of problems, which is obviously what we want, is it unlocks a broad class of problems for the children. So I have tried to pick almost all of my examples, you'll see this in a second, from the MathSpot website, because I wanted to keep myself honest and make sure I wasn't just using easy examples for this. So I genuinely did it as random generator, just picking questions to make sure that what I was saying would work. So some of these examples are messier than others, but I wanted to be honest about what it's like trying to do this. So taking this first one, it's a ratio question, and have a look at the difference. So this might be what you would typically hear in a lot of classrooms where the teacher's been very specific and very descriptive. And they might even understandably be very pleased with themselves because they're saying, I've even shown them how to check. Forget about units, obviously it's just me being quick with it. So this one's focused on a generic strategy around finding what we know, finding what we need, describing how we know what we have, and showing a structure of how we're going to scale up and down. So this is much more focused on broad strategy, identifying what you know, what you need, and a structure that's reliable for doing the checking. Another thing to think about, both planning your explanations and rehearsing, and then when you're talking to the children and you're getting explanation to them, is to keep asking, how did you know? Or to yourself, how did I know to do that? Now, of course, it's not fair to ask the children, how did you know, if you haven't included this in part of your explanation as well. So one of the things to think about when you're preparing your lessons is, how did I know to do that? Because if you can't articulate how you need to do something, how are the children ever going to get there? So let's take an example of this question here. If you're calculating the area, you would know to use base times perpendicular height divided by 2. Or perhaps if it's a part of a trig unit, you might do half AB sine C using the sine of 90, so getting 1. Yeah, just checking I have that right. Versus calculate the perimeter, you know to use Pythagoras because you know you need another length. You know that to get a third length in a right angle triangle, you can use Pythagoras' theorem, given that you've got 2 lengths. If I asked you, can you calculate the value of angle theta? You know to use tan, you know to use trigonometry because you know you're using for an angle in a right angle triangle. You know that you can use SOHCAHTOA because it's right angled. You know to use tan because you've got the opposite and the adjacent. You know to use inverse tan because you're looking for an angle. But everything's I know because. I know because. Thinking, are you clear about that at every stage of your explanations and reasoning? And do you check the children are clear about that in every stage of their explanations and reasoning? Similarly, if the question was slightly altered, the answers to all those questions above would change. Now how am I going to calculate the area? Well, now I need Pythagoras. I didn't need it before, now I do. Why do I know I need it? How can I tell I'm going to use it? Perimeter, same thing. For calculating angle theta, now why is it changed to cos? How come? Those sort of things. So always thinking, I know to do blah because of blah. Is that clear for you? And are you making sure it's clear for the children? Are you making sure it's clear when they say it back to you? One classic thing I'll see as I suppose a missed opportunity, or perhaps called a classic mistake in terms of when I talk about with teachers afterwards, they kind of, when they think about it, is the memory aid, or if you want to say the trick. I'm one of those people, I don't mind if teachers use KFC or anything like that. I don't know, it's really heretical, but it just doesn't bother me. But let's call them memory aids or tricks, whatever you want, is making sure that both you and particularly the students aren't using, saying the memory aid is the reason why something's true. Memory aids are fine, in my opinion, for remembering things and confirming things and feeling confident, but they're also not the reason things are true. So a classic thing I might hear a pupil say, let's say they have this example on the board and the teachers use colors. Give you a chance to read. So people might say, I know the A's go together because they're all purple. But you say, yeah, exactly, they go together because they're purple. That's not why they go together. Obviously, you know that and I know that. And in a way, the teacher knows, of course the teacher knows that, but of course you want the children to feel successful. We have to think, did I care about the child just having mechanical success here? In which case, maybe it's not the right time to push the reason. But if you're trying to push for the children having clarity of reason and cause for what they're doing, you wouldn't want to accept they go together because they're purple. You want to distinguish between, I can remember it by underlining, I can remember it by using colors, I can remember it by highlighting. They go together because they have like terms. I know they have like terms because they have the same variable. So having that clarity in your mind. Typical examples might be something like this. And in this one, I've included the child saying the memory aid because there's nothing wrong with them having little things that confirm it or give them confidence. That's obviously fine. So that's why I've included it. Things that you might want to teach the children to say so they can distinguish between causes and reasons, and memory aids are things like, I can keep it organized in my brain by using colors, or I always remember that it is because of some little trick or whatever it is. So with unlocking questions, particularly AO2, AO3 problem solving questions, some things that have helped us in my last few departments were helping the children with predictions and parameters, which is where the expect aspect of some of Craig Barton's work. This should hopefully, for those of you who are really interested in that, this will hopefully be helpful for how we should break it down even more. Working backwards in a question and helping children to picture things and help them to know you're not looking for a piece of like GCSE art. So predictions and parameters are, I'm going for actually something much more simple than what we often think about predictions as being like really deep reasoning. I'm actually thinking of just almost like simple predictions. So if I was looking at this question thinking, okay, what are some things I know? I know that 15 must be the longest length, but how do I know that? I know that in any triangle, the greatest length is opposite the greatest angle and vice versa. Have we said that to the children? Do they know how to make use of that? So for example, therefore they can see a few things they can predict about this question. They can predict the missing angle must be very small because 93 and 48 almost add up to 180 already. Therefore they can predict that y is going to be very small compared to the 15. The x is opposite 48. 48 is a lot smaller than 93, so expecting the length x to be pretty small compared to 15, but not like tiny, but you know, we're expecting proportion to be a fair bit smaller than 15 and y to be an awful lot smaller than 15, for example. Another thing we'd expect, given what we know about triangles, that x and y must add to more than 15 together. So we could talk about answers that are definitely going to be impossible for x to be 7 and y to be 3. because that would be too small for them to span across the 15. So we could talk about quite a few things that we just expect before we get going, because often if children do it retrospectively and post hoc, they're going like, yeah, because you've already told them it's correct, so they don't really care anymore. So doing some predictions and teaching them how to start doing those predictions through that worthwhile and interesting mathematical technical knowledge allows them to set up some parameters of what they expect. So not predicting, like I can't predict why looking at this, I just know I expect it to be a lot less than 15, but that with X it should come to more than 15, that sort of thing. So I've got some parameters. So that's what I mean about predictions and parameters. You're not predicting the answer, estimating, but you're setting up some expectations. Another one would be, so these are all, as I said before, I now I'm going to use all my examples, or just about every example, from MathSpot, because I wanted to keep myself honest by using questions that weren't of my own picking. So it genuinely was, I went through this, just randomly generate, put it on to make myself do that. And if you've never used MathSpot, Jonathan Hall's website, I recommend it because it's brilliant. So the first one, so then even like a question like S24 is a product of its prime factors, what do I expect my answer to look like? Children might say things like, oh, you're going to draw the tree. So that's what I expect my first working out to look like. What do I expect my answer to look like? I expect it to look like 24 equals something times something times something. I expect to have only prime numbers in that answer, that kind of thing. So that's an aspect of predicting in parameters. Even a question like this, and I'd probably begin by giving them a much simpler version of it, but something like, what do I expect the coordinates of C to be? I expect the X coordinate, have a look at it, it's going to be between 5 and 41. So if I get an answer like 3 something, I know I've gone wrong. So I'm expecting an answer kind of in the middle of 5 and 41. I'm expecting the Y value to be sort of in the middle of 3 and 31. So that's what I mean about predictions and parameters. They haven't really predicted, but they've set up some parameters of their expectations. Give me a chance to read this one. So this one, again, I'd probably begin with a slightly simpler version, just make the numbers super like round and nice and accessible for the kids. But I look at stuff, think like, okay, she has to drive 490. She's already done 175. So she's done more than half of it or less than half of it? She's done less than half of it. So it took her 2.5 hours to do less than half. How long is it going to take her to do the rest? More than 2.5 hours. So it just gives us some little expectations around this question. If you find this interesting, you probably, if this is something you love, you probably recognize this image already. This is from the work of Andrew Stadell, who's a maths teacher in California, who does his website, Estimation 180, is excellent. In particular, I recommend his podcast because it's so thought-provoking and rigorous about how to get children to be better at estimating and forming expectations. And in particular, the episode 3, how to use the range. He has some great advice based on experience and also his deep thinking about maths with children on how to get them to be better at setting up ranges for expectations and not just trying to hone in immediately on like good guess. So if you find this sort of thing interesting, I really recommend Andrew's podcast. So the next step, I'll pause because you'll want to look at the question. So the next thing that helped us with unlocking questions for the children was beginning to work backwards. So if we look at a question like this, and this begins to tap into what it would mean to picture the question, it's showing the children how to simplistically and easily picture the question. Okay, I have to find the shaded area. So just simplistically, no numbers, what is the shaded area? The shaded area is a whole semicircle, take away the little white circle. So let's just draw that. Okay, how would I get the gray semicircle? I need to get a full gray circle and half it. Okay, working backwards, we even do this, like working up the page to show the children, okay, how do I get this gray circle? I need the area of the gray circle. I need the area of the white circle. Okay, what do we need to get area of a circle? We need the radius of the gray circle. We need the radius of the white circle. So you're just working back. Okay, what do I need? Can I look at the question? Still don't have it. Still don't have it. We know the gray diameter. We know the white diameter. Okay, so we can use that. So now can I fill in the next 2 lines? Oh yeah, I can use 11 and 22. Can I fill in the next 2 lines? Oh yeah, I can use pi r squared and pi r squared. Oh, now I can halve it. Oh, now I can subtract it. So by working backwards to all the things you need, then the children can cascade downwards in doing it. And working, obviously this is a process you do together. You might show them a new, similar kind of structure, like maybe a rectangle taken from a square. You can imagine it, but letting them start to do that backwards planning for themselves. Give me a chance to look at this one. Obviously you do a simplified version first. So with this one, I'd say, okay, guys, let's not worry about the first bit. Let's just look, what's the last thing they want? How many boxes for all the units in a week? So let's just write that down. We know that 1 box equals 16 units. So we need to know how many boxes go with how many units. And the highlight is going to be a week's worth of units. So we need to figure out 1 week of units. And let's look at the question. Oh my God, it tells us 5 days. So actually we need 5 days of units. They're the same. We'd annotate that. Okay, can I get a day of units? How can I get 5 days? A day of units? Okay, so I need 1 day of units. That's a, sorry, bad animation, 9.5 hours to make clear that's the same. Okay, what do I actually know? 1 hour is 48 units, and then we can just start cascading downwards. So again, it's backwards planning, and of course begin much more simply, but the same idea. And then from there, it's quite obvious from what to do, but they can see why every step of it made sense, rather than it being you're taking them through a journey, you're opening doors, they're like, oh, it's a surprise, more that you're showing them what the whole journey is going to be, and then off they go. I say show them, obviously they're reasoning with you. So this one's like horrible to look at. You might just want to like tune out for the next few seconds. This is like the most horrible kind of question to do with the students. You might want to pause for 2 minutes and do the question yourself. So assuming you're ready or have decided to tune out, the big thing, so this one I decided to do an honest record, not cross out the stuff that I'd skipped. The first thing I would establish for the class is, okay, we're working out Kieran's speed. To get Kieran's speed, we need his distance and his time for the same amount of, we need the distance that goes with a certain amount of time. And we can take if we have it. And I ticked, so I said, yeah, we know it's 60 kilometers. And then I looked at the question just as like actual me or as teacher me, both be the same here. And I thought, oh, actually, I don't have any information to go with him for 60 kilometers. They just don't give that to us. And that's why I put an X. And I had to talk about that with the students. Obviously, we'll do a simpler version of this first. And I say, okay, well, what do we know instead? We know we need to get his distance and time for a certain set together. We know Z's, Zulkarnain's total distance and time, so you can find their speed. Okay, let's look. Is there anything where we do have something for him? Okay, we know he does 15 kilometers. If we can find his time for 15 kilometers, then we can find his speed. And also you go down there. So you can find the distance and you can see the working out from there. I'd already talked you through a question, how to do it. A specific thing I might have added in to help the students see it would be, for example, drawing the length of 60 kilometers and showing that Zulkarnain had taken 2 hours. We know that Kieran started later, so Kieran's going to take less than 2 hours. I might draw for the X for 15 kilometers to show that we do know the comparison there, that Zulkarnain takes X time, Kieran takes X minus 5. So I know my key is I want to find X. So if we find Z's time for 15 kilometers, then I can find Kieran's time for 15 kilometers and tick, I've got time, I've got distance, therefore I can get speed. So this is obviously a very complex, probably a 5 marker. So it's not a great example here, but I prefer to keep it in just so you can see that this isn't like a magic wand, but it is a way that all this pre-work means that this becomes a more strategic conversation with the children with a few techniques to help it not just be, I've shown you, let's just move on and pretend it never happened. So I'll give you a minute to look at this. So this one is something slightly different, which is picturing and predicting, which is I found that for a lot of students, particularly kind of anyone outside the like 5 strongest in the year group, doing very simplistic pictures really help them to relax into a question. So what I might do is say, okay, let's just read the first bit. Can we just draw a really simple picture to picture this? Sarah and her 2 children are going to Bristol. Okay, what do we actually need? Do they mention Bristol anywhere else? Okay, so it doesn't matter. Do they mention the train anywhere else? No, it doesn't matter. Okay, fine. So we just need to know Sarah and her children. Let's draw them. And we draw them. Let's just put the information and I'd show them we can cross off line 1. We don't need to read that ever again. Then they feel kind of good because there's like not much left to read. Okay, adult ticket 24, child 12. Let's write that in, cross that off. Oh my gosh, we've gotten rid of half the sentences. We've done half of it up. I mean, obviously we haven't done half already, but they feel good. And let's just see, what do we know already? That will cost £48. We know she gets money off, so let's annotate. We know our answer's going to be less than 48, so they can have that sense of progress with very easy mathematics so far. Then let's fill in the next thing they tell us. It's a third off for adults, 30% off for children. Let's fill that in. We can cross that off now. So they have a real sense of progress through the worded question. And actually, they're just rewritten in a more accessible form on the page, but you're showing them how to structure, so it's not just sort of madness on the page. Then you'll do some calculating, and also you're showing them some structure, but what's the big thing is you've shown them how to translate some quite dry sentences into a structure they can actually imagine, and you've shown them how to do very simple images that guide their thinking, as opposed to the kind of confusing and overly detailed images they might tend to without that kind of guidance. So as we know that a lot of time we say to the children, oh, draw a picture, we don't show them how to draw a picture. It's always post hoc. So showing them in advance how to use draw a picture to turn sentences into images and into calculations can really help them out. And this one I had to really think about it as an example of picturing and predicting. So give you a moment to read. So a big thing on this one actually is picturing is really important, but a big thing is often we'll draw these and we don't make clear which bit's the polygon and the kids can't really tell. So I've put some colors they can imagine, and I've annotated inside polygons so they can actually tell what's the interior and exterior of the polygon. So that's one small thing that has really helped me with my students. And the approach we've always taken with these kind of questions is to set it up as a ratio and just use X to represent the value of a part. So 17X and 1X, and annotating interior and exterior. So drawing a picture so they can imagine it. And then we get to work through we discuss our strategy and go through it. And again, I draw pictures to show what I've got. And then obviously our pre-existing work on the formulae. In terms of predictions, something I might have done potentially beforehand, potentially afterwards, depending on the group, and if this would be appropriate, potentially not at all, would be this aspect of predicting. We might have looked through this, probably we'd have gone through this pattern before of the ratio between the interior and the exterior, and how as the number of sides increases, the ratio of interior to exterior massively increases as well. So if we know this one's 17:1, we're expecting a really big number of sides, really big, you know what I mean, relatively speaking. We could even do a few little predictions, like if there's 10 sides, it's 4:1, if there's 20 sides, it's 9:1. Oh my God, there's so many sides. So you've got a sense of like, okay, I'm expecting a pretty big number for the number of sides. So we've gone away from these idea of strategy, going from the specific to the general. So now I'm going to look at specific things to do with instruction and implementation that you can hopefully use. So the first thing I'm going to focus on is syntax. That's the grammar of maths and structures. The next thing is vocabulary and concepts, how you introduce them, and how to make the implicit explicit. Well, some ideas on how to make the implicit explicit. That's basically all of maths. So I haven't solved it, but I've got a few ideas. So the first one's syntax. One thing that we really noticed for our students was they're making these kind of mistakes. And I'll give you a moment to read them. So this was just something we've written as a little summary sheet for the students to help them look back at some of the classic mistakes. So it's obviously this in itself is not a very good learning tool. It's more just a summary tool for us and for them. I'm sure some of them you're recognizing. So going through something like this, also this covers a whole bunch of things around translating from relationships in images or in English into showing them algebraically. So some of the approach we took with this was to really drill down and make it very drill-based initially. Now, one thing I want to get across here before I show these is obviously the purpose of maths is not just to be mechanically correct with what you do. Obviously, just fluency is not the only point of maths. Obviously, just like with football, the point is to actually play the game and enjoy what you're doing and be creative and free with it and be able to make your decisions and have meaning attached to what you're doing in maths. But just as someone like Messi is obviously playing in that kind of way of football, what he does when he actually prepares for that complex, interesting play is incredibly focused, isolated drills. Also, he's not a professional footballer, one of the greatest of all time, because he does these sort of in and out drills. But that isolated, focused practice on specific elements is what allows him to get that level of fluency and creativity on the pitch. Similarly, because I'm not sporting that way, for me, I think about something like that for me would be something like cookery, where I feel really comfortable and free with what I'm doing. But actually, that's because each underlying thing has been practiced to the extent that I don't feel any intimidation, usually, when approaching a new recipe, because I know that I just will know what to do when I'm chopping an onion. It's not going to take any extra effort or energy. But actually, my mom's a cook. She spent most of my childhood just making me practice chopping onions quickly and safely. I know the different way I'm going to hold the knife to chop herbs. I'm at the stage I can just, lots of people are at the stage they can just listen and they can tell if things are cooked or if they need more time and they heat up or down. Even something like you say, oh, you need to learn how to have instincts for it. Instincts for tasting are really tricky without experience and instruction and focused in on learning how to taste food as you go or learning when it's going to need more salt at different stages. What I'm trying to get at with that is saying, I'm about to show you some stuff that's really focused on isolated skills. And I think it'd be a shame if the takeaway is, this is taking all the meaning from maths. These are deliberately stripped of meaning. Well, not all meaning, but stripped of context, because the idea is to get good mechanical fluency at the most basic level to get to that more interesting, meaningful place. So that's why, or contextualized place. So something that I'm particularly focused in on for the children with syntax and structure, with algebra, for example, was how hard it was to compare two things. So even just thinking about the difference between x minus 5 and 5 minus x, there's so many ways it can be stated. And as you can see in these examples, some of them x is first, some of them x is second, and that's very confusing for everyone, especially the children. So in particular, we realized there were four most common ones, which was A take B is A minus B, A subtract B is A minus B, but A less than B is B minus A, and A from B is B minus A. And that was the source of a lot of difficulties for children with both algebra or any kind of shape problem where they're finding differences, and a lot of worded problems. So we've realized we really want to hone in on the specific underlying things going on in order to let them get back to those contexts. So some of the exercises we did, I'm going to show you here, and you'll see just like how many different exercises we did with the children. So we did lots of practice, lots of explanation, lots of mini whiteboards. And here are some of the kind of drills and exercises the children were doing. And again, to reiterate, of course, this would be after lots of checks on mini whiteboards. Might be a lot more of it done orally, might be lots of checks as they're going along, so not just practicing making mistakes. It's just to show you some of it. Adding in a bit of complication, for example, two things are happening at once, decrease it by 2, then decrease it by 7. This is like overwhelming for you to look at. Things like asking them to write their own sentences, give an expression, choose between different options, which ones to represent. Looking at true or false, where they have to just look at something and think, does this seem right? Ones where there could be more than one correct answer, more than one incorrect answer. And even more, they're to translate now from English to algebra. So you've seen all these. So this is, and they were the exact same when you're practicing with multiplying terms, dividing terms, so loads of different things. This is just to show you the sort of things that helped us get to this place. So the kids being really comfortable with algebra and really comfortable forming expressions did take a lot of underlying rigorous drill work. So it's just to show you what some of that looked like. But new vocabulary and concepts is something quite different. That's actually not about drill work, which is we found that making them contextualized was much more effective than using definitions, with exceptions, of course. We found that, so for example, something like this, showing them how powers worked, trying to do it with definitions is very confusing, or even like generalized steps actually is confusing. Just showing them examples to look back and forth with was much more useful to them. And then focusing on variation and structured use was more useful for us checking and for them embedding. In particular, when asking for explanations, instead of asking for technical definitions, asking how do you know to do it? Because, so as we talked about before, I know to do blah because of blah, being the most important thing for you to say and for them to say. And I'm going to show you some examples of how you might get the children to rehearse the use of the new concepts or new vocabulary. So as you saw, here's the example you might show to the children. Then you might put this one up with blanks, ask different children to either tell their partner what's going to go in this blank or to tell you what's going to go in this blank. And another one just in case, including some interesting things like the power of 1, what we expect for that. You might then go into generalizing quickly, introducing this vocabulary as well, just keeping it pacey. Let's just practice labeling different parts. Talk to your partner, making it really structured. What sort of language do I want to hear? Making it very honed in on what's similar, what's different. And then also you're listening into what they're saying, getting full sentences from them, which I'll talk about more in a minute. Perhaps here on the next bit, you want to introduce these as a definition, index form or expanded form or product, really hard to define, very easy to see. So you show them this. Okay, what's going to go in each of these blanks? Going around the room asking, perhaps rehearse with their partner, perhaps showing it on whiteboards. Give you a moment to read this. One thing as well that we realized was really important was as you introduce any new concept was to think, could this be dislodging or confusing a previous concept? So for example, if you've taught them how to simplify using powers, you now need to check that they haven't confused it with simplifying by collecting, in this case, sort of collecting like terms. And obviously we'd show an algebraic version next. So making sure the differences between two superficially similar things were very clear still for the children. So I just want to look a bit more deeply at this idea of the technical definition versus it being used in context to show why I have a preference for thinking, well, why I think from my experience one is more effective for the kids than the other. So here's some examples of a technical definition for a factor or prime. And also those are fine and they do work, but I find that the children, they're a bit like, wah, 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 like they can't really hear what you're saying because it just sounds a bit like blah, blah, blah to them. Whereas things like 2 is a factor of 6 because 2 times 3 is 6. An example of a factor of 20 is 5 because 5 times 4 is 20. So doing things more, this is this because of this, through multiple examples. Potentially non-examples doesn't always help. Sometimes it does. It can be easier because actually most things in maths are concepts rather than definitions. Similarly, here we've got non-example, example of a prime, non-example of a prime, then you ask the children to say the same. So if, for example, you've used these examples, given these definitions through use to the children, you might want to check if they've understood. You might be using knowledge organizers in the way we used to use knowledge organizers, which were only a very small part of what we did, but the way we would have checked for knowledge would be, define it. And we realized that it was really hard for the children to remember definition. They weren't taking meaning from it, and it wasn't helping them transfer. And actually it's better to get them to practice examples and recall examples, because then they could transfer from those examples. So these are the sort of questions you start changing to. Which isn't to say we never ask them to define things, like an integer is worth being able to define an integer, but a lot of things we realized contextualized structured use was much more useful for teaching and for checking. So this is the one that I think it's all game changing. So this is just another one I think is really game changing, is how to make the implicit explicit. So full sentences are not just like this literacy drum that gets banged. It's really important for their maths. Avoiding pronouns, not all the time, but I'll show you what I mean by this. Giving full explanations as you go. So again, this time investment, and reversing the question. So full sentences, we know in maths everything is about the web of connections, about how different ideas are connected to each other. And a full sentence is how you rehearse, and in your case as a teacher, examine the children's understanding of the connections between those ideas. So a lot of the time, the things that we say or that we accept for the children are things like this, they're fragments. What we should be accepting is the full connected thing, A because B, A goes with B. So something like, tell me an example of a prime, 5. 5 is not a meaningful piece of information. 5 is an example of a prime is a meaningful piece of information. So when I say full sentences, obviously there might be times where you want short answers because you want a bit of pace or energy in the room, or it could be the culture in the room is not in the right place for the children to speak for extended times, which obviously you want to work towards, but you are where you are, you have to work with where you are. But in general, a full sentence, if you want, what you're trying to do is to build up anything conceptual or anything to do with meaning, a full sentence allows you to examine, does the child connect the right two things together? A lot of teachers, when they've moved to full sentences in maths, have said that it's been quite distressing and depressing for them how when they take the short answer, the fragment, the child's saying the right thing. When they ask for the full sentence, it becomes clear that actually what the child is thinking is quite nonsensical or quite confused. And obviously it can be depressing and disheartening in the moment to realize that the children have quite confused ideas. But then your choices are find out now, do something about it, or find out later when you're marking a quiz or marking a GCSEs, or frustrated that they've got loads and loads of confused things. So my health warning on full sentences is it can take a while for it to be successful, because what you'll probably be doing for the first few weeks, possibly a few months, is actually dredging up a lot of confusion that's been hidden for a long time by us just assuming the best from what we hear rather than knowing the full story. So this is a drawing I had from a student that made me really, because obviously quite funny. So those 160s are not the lengths of that parallelogram, they're the angles. And what this really made me realize was how much I'd been accepting them, that, this, what, those kinds of words had been, both me using them and him using them, had been concealing that he was actually just really confused what we were talking about. So here's an example of a conversation where the teacher is being much more pushy about the child being specific about what they mean. So them, the child can be talking about anything. Like in this example here, this child would definitely start adding up 160 and 160 to get the perimeter. Even then, be careful, one's on the outside. What things do they mean? And if they don't seem sure, that's absolutely fine. Give them some examples of what you think. Include something else so they don't feel foolish if they were thinking something else. Okay, they've given an answer. They did mean the lengths, that's cool. Make sure they can articulate a full sentence. Maybe they don't know how, so just tell them the full sentence. They can practice saying it back. Let them have that chance at success. And obviously don't then be like, wow, that's amazing. It's not, they've just repeated, yeah, great, you sounded really smart. Or great, that sounded really mathematical. That's all you need to say, because it's true. So a thing that's also really important in your explanations is all the implicit underlying reasoning. So as you're doing stuff, saying how you knew to do it. And I'm simplifying this because they are like terms. So let's do this bit first, because we always follow the order of operations. We're using the inverse of +4 because we are trying to isolate y. So always referring back to the underlying cause of why you're doing something. And one that's really big, and it's another one that a bit like full sentences, the first few times it's going to like really stress you out how much it reveals the kids don't really understand. So let's say we have an example like this. So you've shown the children how to use Pythagoras, and or you're doing these different kind of questions, and a lot of the conditions of things we're not very explicit about what conditions need to be in place for something to apply. So for something like Pythagoras, the children say, oh, what's Pythagoras? A squared plus b squared equals c squared. You say, oh, when can you use Pythagoras? And if you're lucky, they'll say when you have a triangle, but a lot of the time the kids are like, you just know, like they'll say, oh, you just know, but they don't really know. They're actually kind of confused when Pythagoras pertains, and it becomes obvious when you get to trigonometry, and it just becomes a massive mess. And then you've done lots of trigonometry with right angle triangles, and you ask them to get the area of the triangle, gone. How to use half times space times height, gone. So one of the things for you to think about is, one, what are all the actual conditions in place when we use something, and are we stating them, and are we checking the children on all of them? So Pythagoras' theorem can only be used if it's a triangle, it's right angled, and you have 2 of the 3 lengths. Otherwise it's not possible to use it. So something like that being actually clear. So when you're asking a question like this first one, find the missing length, how do we know we can use Pythagoras? It's right angled, it's a triangle, we have 2 of the 3 lengths. Okay. What about this question? You'd ask the children, how do we, is this a right angle triangle? How do they know they can use Pythagoras to test this, the Pythagorean theorem to test this? It's a triangle, we have all 3 lengths, so we can test if it's right angle, because that's of the 3 criteria. What about this one? I want to find the missing length. Should I use Pythagoras? No, I don't, because yes, it's right angled. Well, I should have drawn that in. Yes, it's a triangle, but I don't have 2 of the missing lengths, so I can't use it. So being really clear about all the criteria that pertain in a particular case. So a question like this, we often would accept the children saying x is 130 because the angles are alternate, which obviously is acceptable in an exam, but actually what you should push for is the full set of criteria, which is alternate angles and parallel lines are equal. And that's the reason why, because then we get to a question like this, like, are these 2 diagonal lines, well, the ones that look parallel, are they parallel? Because we've just said alternate angles are equal or co-interior angles sum to 180, that doesn't actually tell them that the lines are parallel. Because we've been accepting alternate angles are equal or co-interior angles sum to 180, they're actually missing, because we've not practiced the full criteria, they're lacking the criteria they need to be able to say why these 2 lines must be parallel. Whereas if you practice the full sentence the whole time, then you can see, oh, I've got these 2 bits plugged in, so I know I've got the 3rd thing. So finally, if you find this interesting and would like to try some of it in your own classroom, my advice for preparing on your own would be start with a few quick wins, but obviously go slowly, because as you push for these, some of these really push up the expectations and the standards, and the children can experience more failures. You need to be very gradual and show them what you're looking for, and in particular, be explicit about what you're looking for and why it's because you believe in them. Also, you need to say what you're doing and why you're doing it, and why it's because you believe in them, but check that they can say it back. So if you say, I know that you guys sound so smart, you give things in full sentences, we don't practice it enough, so we're going to push these full sentences more because it's going to help you guys get to grade 7. Why am I going to ask you for full sentences? Jamar, making sure they can actually say it back, otherwise they just experience that you're really tight and really mean and not accepting things anymore, and they feel like failures. If they know that is part of this narrative, if we're pushing to the next level, guys, then you can keep referring back to that. That is part of you believing in them, they can make it. You need to model the way for pupils. So if you're not explaining the reason for things, if you're not using full sentences, if you're not using technical vocabulary, they can't follow you. It's really hard to make this change. That doesn't mean you're not going to be casual and playful and have all the other stuff. When I say, sometimes people think using correct vocabulary means like being really boring or having no personality. You're definitely going to still keep that. You just maybe will start saying substitute or inverse instead of opposite or pop it in or anything like that. Also, a really important thing to watch out for is as you become more specific and rigorous in what you say, it's very easy to start thinking that's what you're hearing from the children. You need to be very clear in your mind that just because you've elevated the standard of your performance, like technical mathematical performance, doesn't mean they've matched you on that. Because often you'll see teachers saying, oh, I always make sure to say X, Y, Z, which is obviously great that the teachers make sure to say it, but are you making sure you get it back from the students without prompting? That's like the actual test of the success. So that's not to say that it's a bad thing the teacher doing it, but knowing that's one of many steps you're trying to get to. Finally, with the class, don't be afraid to do it again. If a child's giving you an answer that you can see they've done the effort, but it's not technically correct, or it's not a full sentence, they've not expressed it well, because you know, poor Jamar, he's just Jamar is a former student who was wonderful, but I feel bad for him. I keep using this as a fake example. Hey, Jamar, I love that you have all the right ideas there. Let's get that sounding really professional. Let's get that sounding really mathematical. Basically getting them to do it again, but saying that I want you to hit this even higher standard so that the praise is meaningful, but not over the top. If you want to work on this with your colleagues, and in particular, I think this is something that can really, at least for me in my experience, this thing can really drive department meetings being much more collaborative, much more meaningful, and really exciting to work on together. Things like annotating the general steps together. So you might be looking at some exercises or examples you're going to do with the students, and annotating the general steps together is great for both paring it down and really focusing together on what matters and how we're going to model things. With your colleagues, rehearsing explanations so that you minimize descriptions is such a great focused way to practice together, and just using this litmus test of how did I know to do that? So how did I know what to do? How did I know to do that? Thinking, have I made that clear at every stage? And looking at that with each other. And the biggest test that really helped us in knowing we weren't being clear enough with our explanations, or that we were being a bit hand wavy, was we noticed that if we were planning or preparing and we were like, oh, if we do this, then they'll just see, or they will suddenly realize, that means you've kind of hoped that the most difficult aspect of the maths will just sort of magically happen in their minds. So it's time for you to go back, start collaborating together, think, okay, how are we going to unpick this and explode it? So for example, for us, they would be things like that A minus B, B minus A thing, which was so hard. And it took a long time to figure out all the exercises and practice we needed to just make it actually happen. Before that, we just kind of like, oh, if they see enough examples, it'll magically happen. That's the time that you know it's going to be like, let's really dig in with this piece of work. So thank you so much for joining me. And I love thinking about this, and I really appreciate Colin asking me to make this video because I love putting my ideas on it together. So if you want to try any of this, I would love to hear about it. Obviously, I want to know what works. I also want to know what doesn't work. Anything to improve this aspect of learning for children, I want to hear about it, whether it's things working or not. And the best way to reach me is on Twitter @DannyCQuinn. Have a lovely day.